message that I heard. So I'm James Foster. We're going to discuss GemStone, and something unique in GemStone is we support class and object versions. And this is a bit different from the traditional Smalltalks, and some people in discussing topics suggested that this would be an interesting area. So, introduction, a brief description of the architecture for GemStone, and then we'll discuss how we do object lookup and versions, then class lookup and versions, and then go to questions. So traditional Smalltalks have an object memory that fits, an object space that fits into memory. They have a single VM that has access to that object space. They share objects between VMs only with difficulty, typically a file out and a file in. And the object state is lost when the virtual machine exits, unless you have some special saving process. With GemStone, we have an object space that is limited by disk, not RAM. We have an object space that's shared across multiple virtual machines. And we have transactional persistence. So how do we do that? A brief discussion of the architecture. We have a repository. The repository is the on-disk representation of the object space and the ultimate record. The image, or repository, is made up of multiple extents. Each of those is a file or a raw partition. And then within each extent is a page, a 16K chunk of memory. We have a gem process. The gem process is essentially the virtual machine for each Smalltalk. There's a stone process. The stone process is the thing that handles concurrency. Anything that can only be done by one process at a time will go through the stone to handle concurrency. And then for performance optimization, we have a shared page cache. While the image and objects are ultimately on disk, memory, of course, is much faster. And if you have multiple VMs that are sharing objects, bringing them into memory and sharing them across the memory space will give you some efficiencies. And there are a number of other processes that are used to handle various other tasks that the system is made up of. Now, this slide is not one that you can read, and that's actually partly the intent. It just gives you an idea of the processes, the log files, the disk files, and other things that go into making up the system that interacts together. So we have the repository and extents. The repository holds the persistent objects. It's made up of from 1 to 255 extents. Each extent can be up to 32 terabytes in size. So to a very large extent, to a very large factor, we consider the size to be unlimited. And when people ask us to test large volumes, we actually say, we'll be happy to if you provide the hardware, because we don't have that much hardware. The extent 16K pages, each page is of a special type. There's a root page, object table page. We'll discuss some of these in detail. The data pages, commit records, and other specialized pages. Each page ID identifies the extent and the offset within the extent to say where to find a particular page on disk. The cache is addressing the challenge that disk access is slow. Now, of course, as more and more people are using SSDs and other faster implementations, that becomes less of an issue, but still we keep an in-memory cache of pages. The cache is divided into frames that are the same size as a page, and you can load a page into a frame. Each frame can be clean, dirty, or empty. There's a list of free frames, and so if you want to load something into the cache, you need to find a place to put it. And so this is done with a free frame list that says here's places that you can put things. There's background processes that write dirty pages to the repository so that then they become clean and can be used elsewhere if needed. And free frame servers search for free space. The gem, again, is the virtual machine that runs Smalltalk code. It represents a single logged-in database session. So each time you log into the database, there's a new gem started. It has its own local memory, as well as access to the shared memory. It executes Smalltalk code and is the virtual machine for you. It reads data from the repository, so it figures out where the data is, and we'll get to object lookups in a moment, and reads data, a page, into the shared page cache, and then copies the information out of the cache into its local memory that it needs, leaving the data there for other processes to use if they wish. And the gem is responsible for creating and modifying objects. New values are created in temporary memory, but then they get copied to the shared page cache, and then coordinated through the stone, get written to disk, and to a transaction log for rollback and recovery purposes. So, object lookup. How do we do object lookup in GemStone? Typically, or this is done through a process, the object identifier is a unique ID assigned to each object. We tend to not reference objects by a pointer. So in most modern efficient Smalltalks, in-memory references are through pointers, and everything points to each other. And we heard mention this morning of when you do a become, you have to scan the whole object space. Well, if your object space is terabytes on disk, that would be prohibitive. So objects can move. So again, all you have to do is update the object table to point to the new location. Different values. Objects can have different values or versions based on changes in a transaction. And in GemStone, we have isolation and repeatable reads. If one session is in a transaction, reads an object, another session makes changes to the object, the first session will still see the original values. So we need to leave both versions of the object existing on disk. We'll look a little bit more. So the two-way become is more efficient since all we have to do is swap the object IDs. Often internally or in the documentation you'll hear reference to an OOP, OOP. This is an acronym for an object-oriented pointer, but of course we don't use pointers, it's an object ID. But that's the terminology that's often used. Though for performance reasons, once an object has been read into memory, it will often be referenced through a pointer, as long as it's in memory, so that we don't have to go through the lookup. Once something's in memory, we can keep track of it more efficiently. Again, this is done through an object table. The object table maps the object ID to a page. The page is, again, the extent and an offset within an extent to this 16K chunk of memory. Each page then has its own minor index to help you find the object within the page. Whenever you create a new object or modify an object, you put it onto a new page. We never modify an object in place because other sessions might have a view of the older version of the object. We create a new version of the object and put it in a different place. Each transaction then creates what is essentially a new object table. This new object table has the list of objects and pointers to where they are. And so as objects get modified, we update the object table and create a new object table for each commit. Each transaction has a unique view, and there is some optimization to avoid duplication, of course, because the object table would be huge. And so to the extent multiple views can share an object table, they will, since most objects don't move for each transaction. The object table, of course, takes up space. And the space is in the repository and in the shared page cache. And space, of course, is not so much expensive, but is another thing that needs to be read into memory and dealt with in garbage collection and other memory management. So, object lookup. Again, the only time you'd ever be looking up an object is if you're sending a message to it. In Smalltalk, we do everything through message sounds. So once some object is in memory, it will have instance variables, named and numbered, and these instance variables will point to other objects. So here we have a reference to an object that will typically be an object ID. And with that, we look up the object ID in the object table to find the page, see if the page is already in the shared page cache. If not, we need to find space in the cache to read the object, read the page. We read the page into the cache, and then we can take the object off the page into local memory. So, versions of objects are based on the commit record. Each time you log in, you have a new database view. The object table provides a map to the extent and an offset, and each view has a unique object table. And each commit creates a new object table and has some other information contained with it that is useful for processing subsequent commits and garbage collection. So the commit record, there is always one database view, at least one, or commit record. So a quiet system that has no one logged in can have a single commit record or view. Once someone logs in, now there's a gem and it obtains a reference to that commit record. That says, when I want to look up objects, here's where I go. Another gem logs in. That gem can share the same commit record. It's a view, a static view of the database that's not modified because this commit record is a reference to a previous commit. So the gems can share it. If this gem modifies things, it will create a new commit record. And so now we have two commit records that have two object tables that could have two versions of the same object. The first gem could do an abort and move to the second commit record. So now they're sharing the next commit. And if no one is referencing a commit record, it can be disposed of and certain data structures associated with it cleaned up. Another commit will create another commit record. So here we've gone to number 3. So now they're on separate commit records. again, we've got 2 commit records, 2 and 3, a couple gems. Yes, Elliot?
So James, are new commit records created explicitly or as a side effect of making a modification or as a side effect of committing a modification?
The virtual machine creates it, so there's no Smalltalk programmer responsibility in it. So it's, in that sense, a side effect of if you've made a modification and if you have a successful commit,
Right.
then the virtual machine will create a commit record. It will add it to the list of commit records, give it to the stone will manage it and share it with the other sessions. Whenever the next session does an abort or commit, it will hand out the thing that someone else created. Okay? Yes?
There is no relationship between the 2 commit records. When you look, it's a copy, you do a copy and you modify?
There is no logical virtual relationship between the 2 commit records. Now, they can share they can share objects if the object versions are the same for both commits. Then they will share those objects. And the object table will be optimized in such a way that it will be largely shared. But each gem, when it is modifying objects, it does not make modifications in its view. It makes modifications in its own local temporary space. And it holds them in preparation for a subsequent commit, where it will then go through the process of creating a new commit record and validating it. When the stone, and again, there's a commit token because only one of these can happen at a time.
So James, does that imply that there is a limit to the maximum working set that one can change? That it's limited to the address space of a gem? Or is there a way of streaming?
Okay, no, it is limited to the size of the gem. And as mentioned earlier, the gem can have configurable temporary space. And for other reasons, it is considered a good practice to try to keep commits small and short. So yes, there is a practical limit on the size of a commit. And many small, you don't want to have churn because there is overhead to commit records, but more small commits will typically have better overall system performance for other people than a few large ones. Okay, so additional commits create additional commit records. And intermediate commit records cannot be disposed of as long as there are older ones. So we can't get rid of 3, 4, 5, 6 as long as 2 is visible. And this can become a problem. And a certain amount of GemStone work, tuning, consulting, programming is avoiding a commit record backlog. This is one of the significant issues. Typically, the goal is to keep it less than twice the number of sessions. So if you have 40 sessions, a commit record backlog of 80 would be a reasonable maximum. And one of the first things a consultant will do coming into a customer site is look at the commit record backlog. And I remember the story someone told of Elliot coming into someone and saying, oh, well, you just moved this assignment before the loop instead of doing it inside. And you know, that solved a week's worth of consulting in the first hour. Well, maybe these stories are exaggerated, but these are the stories that. But I went to one place and complaining of performance, and first thing I looked at was the commit record backlog, and it was over 1 million. And I said, there's your problem. We'll solve that, and you'll be in good shape. We'll look briefly at, yes?
A question about
Yes.
version. So
Yes.
this is, you have not real object versions. It's more a technical artifact of the way you store them permanently. So you cannot go and say to an object, give me all your versions and find me that version where this instance variable had this value.
You are correct. This is not, this is more of a side effect of the implementation that we are doing to handle multi-user management. This is not what a financial auditing firm would want in the sense of how was this done. Now it turns out, not discussed here, is each transaction also creates a transaction log for rollback and recovery purposes. So if the system crashes and not everything's been written to disk, or you lose a disk, we can recover from a backup in the transaction logs. And the transaction log actually does, by its nature, contain each object and each change to each object. And so for financial auditing purposes, and again, this is more historic auditing than online viewing, we have separate tools that can scan a transaction log and find who, when, what edits were made to an object. But again, if you really want to be able to present to your users, if you want the application feature of object logs, then you need to implement it as an application feature. It's not built into the system in that sense. Yes?
I'm sorry, I did not get why can't you discard commit record number 3? Why do you need to keep the whole chain?
Okay. Part of validating future commits is to see if there are changes to the objects. And so if you and I both want to reserve a seat on this airplane, we might get a commit record, we might get a view of the database that shows the seat as empty. If I purchase the seat, and then my change will be in a commit record. If you still are looking at an old view of the database and see that that seat is empty, you want to buy that seat. The system will let you buy the seat, and then when we go to do the commit, a feature of GemStone that you do not have to write into your application code. A feature of GemStone is if you attempt to commit a modification to an object that someone else has modified, your commit will fail. And so we have to keep all the prior commits. So if you are still looking at commit record 2, commit record 3 might have a change that conflicts with what you plan to do when you make n+1. And so commit n+1 cannot conflict with CR3. And so we have to keep CR3. And so this is how it slows down new commit processing, because part of a commit is, have I conflicted with anything between my view and the current state of the system?
But if you've got a whole bunch of commit records that sell seat 3A, can you not garbage collect the intermediate ones?
One could perhaps go through an optimization process of consolidating them. Yes, and if we found a compelling case where it was valuable to the users to have a large commit record backlog, then we could go to the work of making commit record backlog more efficient. But, Martin?
Basically, we could get rid of those intermediate ones, but what needs to be saved is the information in them, and the problem is the amount of information in all of them. So we could unify that information and save some space, but there would still be a problem, and it would take time to do that.
Yes, yes. So, it is possible, but our experience so far is, it hurts, don't do that.
Can one be
notified if
Yes, yes. So we do have built-in structures that we can send a signal saying, by the way, you're holding on to the oldest commit record, and in fact, there's processes you can monitor for signals, so we can send you a notice saying, please do an abort or a commit or log out or something. Yes. Okay, let's turn briefly to classes. So we've discussed objects, and there's days worth of detail here. I'm just sort of trying to whet your appetite for interest. And share some interesting technical things with the technical crowd. Classes. Classes, typically in a typical client Smalltalk, you do a lookup. You have a single dictionary that's the root of all your lookup. And when you compile a method, you do a lookup by saying, find the thing that's there with that name. And you, in the compiled method, you bind to an association, or you can also do a lookup at runtime, say Smalltalk at array new, and that will do a runtime lookup. If you modify a global, essentially you're changing the value of the association. The compiled method doesn't reference the value, it references the association. So when a global gets modified, you still look up through the association to get to the value, which gives you what you're looking for. In GemStone, it's more complicated. Many things are more complicated. We have a root that instead of being a single dictionary, we have something called all users. That is the important main instance of a user profile set. A user profile set is a collection of user profile instances, and the user profile is a description of someone who can log into the session, a user. A name, the privileges, groups, and this thing called a symbol list. This thing called a symbol list is an array of symbol dictionaries. And the symbol dictionary is then the key value mapping thing. So each user has a unique symbol list, but the symbol lists can share symbol dictionaries. So typically globals and something called published are dictionaries that are in everyone's symbol list. And typically each login user will have its own user globals dictionary with that name, but their own local user globals. At compile time, of course, we need to bind to something. So at compile time, we do a lookup. Instead of looking up in the dictionary, single dictionary, Smalltalk, we search through the symbol list that is current for the user as they're logged in. And then we have this sequenceable collection of symbol dictionaries. We look through them until we find something, then we bind to that association. There's a current symbol list that is used if you don't specify one, but you can build a unique symbol list for the compiler. So you could pass in something else. And this would be an opportunity for the tools, the IDE we've grown to know and love, to create a unique symbol list. And this would be an area where one could develop a package management system, for example. And when you go to the compiler, you say, when you're compiling methods in this class, here's the symbol list that you use. And it contains things that we're going to look for. Each time you log in, you have a user profile that is from the disk. The symbol list comes from the user and is by default the one that is associated with the user on disk. So when we do a name lookup, we could also do it at runtime. So you could say something like system, my user profile, symbol list, object named array, and then new. Or you could say globals at array, Or you could say user globals at array. And that would give you either the same or a different array. So you could override, you could have a completely different class named array. And if it was visible, then you would use it when you compiled your methods that had that symbol list. So, class versions. Again, in traditional Smalltalk, when you're modifying a class schema, adding, removing instance variables, you do have an atomic operation where you make the modification, you find and migrate all the instances that are just in memory, and there you have it. If you drop an instance variable, you'll just lose whatever value was there. In GemStone, again, things are a little more complicated. We have to leave old objects there because they may be visible to other sessions, and we can't modify them for a consistent view for an existing login. And it would be too large to scan. The database may be too large to scan. So we leave the old version of the class. Although tools might say, if you modify a class, do you want us to scan and migrate everything? And then you can say yes. Editing a class schema creates a new class. May or may not have the same name. The prior class's methods can be copied into the new class. Some may fail compiling if they can't find an instance variable. The new class is added to a class history. We have something called a class history that is a list of classes associated with a class. And the new class then can be added to a symbol dictionary. And the old class still remains, and objects that reference the old class are still instances of the old class, and have the old behavior, and have the old methods. And it's common to look at code and say, I have a halt in this code, but it's running through it without halting. It's kind of, oh, it's an instance of that class, but it's a different version of the class, so it's executing a different method, and one that doesn't have a halt in it. And it can be the same except for the halt, and it's very confusing sometimes. Each class references a class history. Each class is also in a class history, and it provides useful guidance for migration. Migration can be explicit, needs to be explicitly asked for. You can do it on an object-by-object basis or all the classes. And there are methods in object, particularly, most significantly, the migrate from with an inspar map is a method in the new class version that you can have called, and it will say, we're about to create a new one out of this old one. What would you like to do? And so you can actually move instVars around, combine them, create new defaults based on old values and things like that. So you have a lot finer grained control over what you're doing here. And then in the object table, we swap the identities. So, I've already taken, I think, most of the time. So I'd be happy to entertain one or two questions, and then we'll be around. There's other here, Martin, Dale, Norm Green, and myself. We love to talk about all of these things. Yes?
Are these migration methods called automatically, or?
Yes, there's default implementations. So the default implementation is copy all the values that, all the instVars that have the same name, copy the values straight across. All the instVars that don't copy across, drop. And all the instVars that don't have, a reference, just default to nil. So, and it gets called. These methods, only if someone sends the message migrate. So you can migrate object at a time, or under class, there's migrate instances. So you can say, collect all the instances and then migrate them as a background process. Here? Uh-huh.
Is GemStone implement fork method on block order?
Is GemStone
Implements fork method.
fork? It is possible to fork a block, yes, but it does not create a new operating system process. It is essentially a green thread inside your existing virtual machine, which is similar to the way other client Smalltalks work. But the forked block will be inside your virtual machine and will have your same view, and can only run if other processes are paused. Elliot?
James, I guess if you're doing a complicated migration, you'll want to test it.
Oh, yes.
And so you'll get some number of versions that you don't want, and you will have created new versions of it. Or is there support for, like, you know, you do some things and then you throw away all those intermediate versions, or do they just always lie around?
Well,
Or do people just miraculously get it right?
well, I mean, one thing is, you know, you make a backup of production and then do testing in your environment. Each time you migrate, until there's been a garbage collect, the objects will just sit around. But if they're no longer referenced, that is, if you've done the become, then the next garbage collect will just take the objects away. And so, if, for example, you have an inst var that you need but forgot to add to the, you know, carry across, then you may be able to find the old objects, but it would be not something you should rely on. Yes.
But do you still have to commit or?
Oh yes, yes.
So you're in a transaction.
You're in a transaction, yes, and you can certainly go to a backup, restore up to just before you started migrating, and find them. And again, until you do a garbage collect, they're going to be on disk somewhere, and all instances will find them.
I had problems with that. Very annoying. The first object goes right, second object goes right, and the third object is gone.
Okay. Again, we'd be delighted to talk about this more. Favorite, you know, enjoy these sort of technical discussions. But